Okay, so the topic for today is minimum cost flows, which are generalizations of maximum flows, shortest paths, everything that we've discussed. So what we're going to do is discuss a linear programming algorithm to solve the minimum cost flow problem. Now, if you recall, for the shortest path and for max flows, we gave combinatorial methods, whereas here we are just going to look at how the simplex method would specialize when it applies to this class of problems. There are combinatorial algorithms to solve these problems, which unfortunately are not discussed in your text, and so we won't discuss them in this class either. But it's not too difficult to see how they might come about, and if there's time towards the end of the lecture, I will tell you what the structure of a combinatorial algorithm for this problem might look like. Okay? So basically what we're going to do is take the simplex method and observe what happens when it's applied to this class of problems, which are highly specialized as compared to general linear programming problems. Okay? So that's the idea of the lecture. Now, once again, I think your textbook has a somewhat interesting way to treat this issue. I think it just tells you what the various elements are, what a basis is, what the reduced costs are, and so on, without actually going through the algorithm on an example. At least I didn't see it. So once again, you'll have to rely on slides and what we do in lecture to really understand what's going on. And if this is incomplete, or if I find that you haven't understood it well enough by the end of this lecture, we'll come back to it, or I'll prepare a set of notes so that you can read and follow. Okay? So let's actually go through a couple of quick examples that we've already discussed before we get to the algorithm. So this is, if you recall, this is the minimum cost flow problem. You have arcs that have capacities as well as shipping costs or flow costs. Okay? And so you'd like to minimize the overall cost of the flow. The x variables indicate the flow. Your flow has to obey capacity constraints, so the xij's have to be smaller than uij's, and they have to be non-negative. And you have these BIs, which are supplies or demands. So BI is the external flow into node I. And what this says is really that if you look at all of the flow that leaves node I minus all of the flow that enters node I, so this is the net surplus at node I, that has to equal the external supply. Okay? So whenever BI is positive, it's viewed as it's a real supply. When BI is negative, it's a demand. And so you want these constraints to be satisfied at every node, and you want to find an optimal solution subject to all of these constraints. Okay? So this is the problem. Now, unlike the maximum flow problem, it's not even clear that there is a feasible solution to this problem, right? It's perfectly easy for you to find situations where it's not possible to satisfy all of these constraints. Right? Does everyone agree with that? If it's positive, it's a supply. If it's negative, it's a demand. And I think this is what your textbook follows as well. But one could just as easily do the other way around. Nothing changes. So notice also that this is a linear program with a couple of unusual features. So first of all, it's a minimization problem, whereas we've always worked with maximization problems. Secondly, you have variables that are constrained. So variables are not just non-negative, but they are upper bounded as well. Okay? So they have to be at most a certain quantity. So these are two features of this linear program that we didn't really have when we discussed general linear programming problems. Of course, the first is very easy to fix. You could just write it as maximize the negative of all of this. The second is also easy to fix. Because you could say that I'm going to take all of these constraints, xij less than equal to uij, and regard them as part of my constraint set. So in effect, what I have is a linear program that looks like all of this. Yes? So, let me see if this is a fair one. Now I don't see, there isn't an extra one here. Okay, good, yes. Okay, so let me take this opportunity to review other things that we've already discussed. So first of all, here's a little example to show that if you want the shortest path problem is a special case, right? So we've already seen this. If you want a shortest path, you just give a supply at node 1, a demand of 1 at node 6, and you solve them into a flow, and basically you get what you want. The maximum flow problem is also a special case where you could add an extra arc from T back to S with a cost of -1, and there are no supplies or demands. And so, because there are no costs in the maximum flow problem, just capacities, if you have this red arc with a cost of -1, every other arc has 0 flow cost. So if you want to minimize cost, you would like to maximize the amount that flows back from T to S. And anything that flows back from T to S has to really go from S to T, because all of the supplies and demands are 0. So if you want to send 10 units back from T to S, 10 units somehow have to flow from S to T in the original network. And therefore, that is why the maximum flow problem is a special case. We discussed transshipment problems, which are transportation problems where you may have nodes come off, right? Was the right way? No. No. Okay. Sorry about that. Okay, so there are transshipment problems, which are transportation problems where you have some intermediate nodes. So, for instance, in this little example, there are plants that produce things that can send stuff to these blue entities, which are warehouses that ship them to retailers. So if you have a transportation problem with this property, that also reduces to a minimum cost flow problem in the obvious way. Here's a little more involved network problem. So this is called a caterer problem. It's sort of an old, a classical problem that was realized to be actually a minimum cost flow problem. So suppose you have, you're a caterer, you have a demand for so many napkins every day, and these are reusable ones. So, you can buy new ones that cost you $8 cents each, and you could actually send the dirty ones to the laundry, and there's a slow one that costs you B cents per napkin, and there's a rush one that costs you slightly more, C per napkin. Okay. So you want to satisfy all of the demands, and you want to spend as little as possible. So, you may, if you have successive days in which you have huge demands, then you have to, because there's at least a 1-day gap between getting the napkins cleaned and using them, you may have to sort of have more napkins on hand. On the other hand, if the demand is uneven and you have peak periods followed by not so peak periods, you may in fact want to use just the 2-day laundry and somehow solve this problem. So at any rate, it's not clear a priori what you would do. How many napkins should you buy, and how many should you send to the 2-day laundry, and how many to the 1-day laundry? And of course, this could change over time, right? On a certain day, you would want to send a certain amount to the slower laundry, a certain amount to the faster laundry, and so on. So the assumption here is that the demand follows a pattern. It's the same every week. And so you have these BIs over 7 days, and that repeats over time. There's a question here for everyone. So how would you solve this as a minimum cost flow problem? Yes?
We compare the cost of and find studies.
You compare the cost.
Compare the cost if I take on 1-day laundry. For 1-day laundry, I do 2 days work, and then I take 2-day laundry and see the cost, and then do the buy new napkins strategy and see how much it costs for me if I do the 2 days.
Okay, so that's a good start. So you sort of look at each of these strategies in isolation and figure out the best one. There's no reason why you can use one or the other, right? I could send a portion of the napkins I have to the 2-day laundry, a certain portion to the 1-day laundry, and a certain portion I could just throw away. In other words, there's a combination of things that I could do which would not be covered by what you're suggesting, which is either use only the 2-day laundry always, or use only the 1-day laundry always, and so on. So your idea sort of comes from some of the homework problems where you do these kinds of things. Okay? And this is, the next level, slightly more involved than that one.
That's exactly what I.
Okay, good. But the solution is not much more complicated than what you said. You will try a little bit. Yes.
Yeah, so it seems like you would have maybe a series of nodes for each day. And then for the 1-day laundry and the cost of new napkins, you would have a pass from to connect each successive day.
Right.
However, the 2-day laundry would skip each successive node.
Right. Very good. So you have a sequence of nodes. That's one for each day. And then you figure out, stuff that you send to the 2-day laundry is not going to be a supply for not tomorrow, but the day after that. Stuff that you send to the 1-day laundry is going to be a supply for the following day. That's good. The only other thing that you should do is have these nodes separate for clean and dirty laundry. Like you could have clean napkins that are unused on a certain day that you could use the following day. And so that motivates the following construction, where you have something like this. Okay? So here are the nodes that represent clean napkins, and here are the nodes that represent dirty napkins. So if you look at node 1, you want at least D1 units to flow on this arc. Okay? because on day one you use D1. That's your demand. Okay. So now you have flows. You have a network flow problem in which there's a lower bound on flows. So presumably you could sort of spend, or you could spend more than what is necessary, but you wouldn't. So there's a lower bound of flow on this arc from 1 to 1 prime, which is D1. And likewise for all of the other arcs. Okay? Now the blue arcs represent sending the dirty napkins to the one-day laundry. Okay? So anything that was dirty on day 1 would be sent to this one-day laundry and would become clean at the beginning of day 2, and so on. The green ones represent stuff that's sent to the 2-day laundry. And of course, you could store dirty napkins, but just not do anything with them. Presumably, they don't get dirtier just by being there. So those are the red arcs, and of course, you could store clean napkins, and those are the red arcs on top. Okay. Now, this problem, as formulated here, is only a 7-day problem. So we're not doing this periodically, as I said we would be. But if you were doing it periodically, you would have an arc from 7 prime back to 1, and so on. I mean, there would be a blue arc from 7 prime back to 1, etc., etc. So anyway, so let's actually go through this construction very quickly. So one can purchase napkins at a cost of A cents per napkin. So the green nodes are going to represent clean napkins, and that's the node that represents purchase. So you could get flow into any of the green nodes from node 0 by paying A cents. Okay. So those are the flow costs for napkins on those arcs. The fact that you must use DI napkins on day I means that you have a lower bound on flow. Yes.
Can you just throw something away? Or
can you throw
the dirty napkins away?
Yes, you could just throw them away.
But would it be like then like D1 like you are sending to the laundry?
No. So you will see how that's taken care of. Okay? So suddenly you have lower bounds on arc flows in this example that we have not seen before. So you have the same for all of the 7 nodes. Yes?
Well, I guess these would be upper bounds as well, unless you were like throwing your napkins in the mud, right?
Yes. So these would be, so in other words, so the point is, why would you send more than D1 units anyway? There's no reason for you to send more than D1. That is true, but you don't have to worry about it because the fact that you're optimizing costs would take care of that. So purely from a modeling perspective, you just need at least DI napkins. You don't need exactly DI. But you could think of that arc as having both a lower bound of DI and an upper bound of DI, in which case the flow would be exactly DI. But you don't have to enforce the upper bound. So the rest of the arcs, you may launder napkins in 2 days at B cents each. So you have the green arc from 1 prime to 3, from 2 prime to 4, and so on. And the one-day laundry, you have these blue arcs from 1 prime to 2, 2 prime to 3, and so on. And finally, you can store the clean napkins for free, and you can store the dirty napkins for free. So there's a question about whether you could just throw the dirty napkins away. You could just throw it, in which case you can have some sync node that just collects all of the napkins that you don't want in the system. But right now we're just assuming that anything that is not laundered is just stored. The stored where, you can just think of it as stored in some place where you don't care. Yes?
How do you account for laundry put in for 2 days on day 6? How does it come around?
Okay, so this is a static problem.
So we're just looking at a 7-day problem. So on day 6, you would never send anything to the 2-day laundry because that's outside your planning horizon. But if you were looking at this as a periodic problem faced by the caterer, then you would have an arc from 6 prime back to 1. But of course, that means you're just looking at this in steady state, whereas now we are beginning from scratch. Any other questions? Okay, so this application to airline maintenance, and I'm going to leave you to figure out, what that might be. So, I mean, you can think of, and this is something for you to keep in mind. That models with this structure come about all the time, right? You have certain entities that need to be maintained, and you have, preventive, you have maintenance of various kinds. Right? You could be very, very conservative, in which case there's a very, very low probability of something failing, therefore you're having to spend an emergency maintenance. So you could think of routine versus emergency, and you could think of the costs associated with each of these, and so on. So even though it's phrased in terms of an application that seems trivial, it actually comes up in many situations. Okay, so now some of the assumptions we make when discussing minimum cost flows are that all the data are integers, and this is something that doesn't have to be true, but just makes it convenient. We're looking at a directed network, and we saw that any undirected network we can convert to directed networks by, you take an edge without direction and replace it by a pair of edges. We are assuming that there's balance. The total supply equals total demand. Because we use positives for supplies and negatives for demands, sum of all the BIs is 0. If this is not true, you cannot have a feasible solution. That should be easy to see. If this is true, you may still not have a feasible solution. And we saw some examples of that in the previous lecture, where you had a maximum flow problem, or you had a matching problem where you wanted to match all 4 people to 4 jobs, except that 2 of them could only do a single job, so 1 of them had to remain unmatched. So you could have situations like that where you cannot meet all of the supplies. I mean, if your network is such that, let's say you have a node with demand of 10, but nobody connects to it, then there's no way this demand is going to be met. That's a trivial example where you could have something like this and not have a feasible solution. And of course, we assume that there is a feasible solution. One needs a method to detect when you may not have a feasible solution, and we won't worry about that for now. So let me just skip this and come back to it later if necessary. So in telling you what the simplex method would do, remember our goal is to take the simplex method and specialize it to this network flow problem. So what are all the elements of the simplex method that we need to revisit? First of all, we need to know what a basis is. Right? What is a basic solution? And then we want to know how to do it. So remember, in the simplex method, we start with some basic solution that's feasible. Then you write down the dictionary. Look at the last row of the dictionary. That's going to tell you which non-basic variable is going to be attractive to be entered into the basis. And then once you decide which variable enters the basis, you have to pick something that leaves the basis. Then you continue. So we want to know what a basis is. We want to know, let me write these things down. So we want to know what a basis is. second thing we want to know is choices for the entering variable. For the leading variable. So these two fall under the title of pivoting. So you want to know how you would pivot, how you would go from one basis to the next. And of course, finally, termination. Or in other words, what are the optimality conditions? I mean, I'm writing these separately, but they're all intimately related. So for instance, the way you figure out which variable enters the basis, you know, that test would tell you when you're at optimality. If there's no variable if there's no variable that you can enter into the basis, then you're at an optimal solution. Now 0, of course, is initialization. And we are not going to discuss this for now. So once we sort of know what these things are, we know how to apply the simplex method. Okay? Does everyone agree with this broad outline? So the rest of the lecture, we are going to discuss each of these things and see how everything goes. Now, if you recall, the way we decide which variable enters the basis is to figure out what the reduced cost of every non-basic variable is. So we want to know what the reduced costs are. And so basically, the reduced costs are given by this expression Cij minus pi I plus pi j. Cij is the cost of the arc that you have. And the pi's are dual variables. So there are going to be prices on the nodes that we are going to come up with in a little bit. So this is just to convince you that there's a very simple expression for computing the reduced cost. And so if you can find the pi's, then you can evaluate the reduced cost of each arc and see if it is of the right sign. If it is of the right sign, then you would consider introducing that into the basis. The second thing is optimality conditions that we get into in a little bit. Now, let's actually understand what happens when you, instead of the original cost, Cij, you change the original cost to these reduced costs. Okay. So I'm going to, instead of Cij, what I'm going to do is take Cij, subtract away some number pi I, and add some number pi j. I don't know what these numbers are yet, but just think of them as certain numbers that you obtained in some way. The claim that I want to make is whether you optimize with respect to the original cost or with respect to the reduced cost, you're doing the same thing. In other words, rather than look at the network flow problem where Cij's are my costs, I could actually look at it as cost Cij pi, and my optimal solutions are preserved. This is the analog of saying, remember when you go from one dictionary to the next, whether you look at that LP or this LP, you're solving the same thing. Loosely, it's like that. So why is this true? So notice that for every unit of flow out of node I, you subtract pi I from the cost, and for every unit of flow into node J, you add pi j as a cost. So if you look at this little example, those are my original costs, 3, -5, and 1. And I'm going to think of the cost now as 3 minus phi 1 plus phi 2, 1 minus phi 2 plus phi 3, and so on. So if you compute the overall cost of your flow, then it must be that the pi's sort of get multiplied by the b's somehow, right? I mean, ultimately, let me actually do this fully on the example. So if I look at this expression, C times x, this is the original C, and C pi times x. So I take any flow x, okay, and I look at its cost on the original network and its cost on the transformed network. So remember that Cij pi is Cij minus pi I plus pi j. So when I look at the flow on arc ij, it's going to be Cij xij minus Cij pi xij. This is the term contributed by arc ij in that expression, Cx minus C pi x. Now this quantity is just pi I minus pi j times xij. Okay? Just simple algebra. So that's what this expression says. But now you can separate this out in the following way. That if I collect all of the, if I look at the coefficient of pi I is going to have a positive coefficient, pi I is going to have xij for everything that leaves I. And it's going to appear with a negative sign for everything that enters I. So again, when you go from this step to this step, it's just algebra. So you're just collecting all of the x variables that multiply pi I. Those flows that leave node I will have pi I with a positive sign. And those flows that enter node I are going to have pi I with a negative sign. And that's what this shows. But we know that flow is conserved at every node. So this quantity is just going to be bi. And so this is just going to end up as sigma pi I bi, which, if you recall, is just a constant because the b's are data. Okay? So when you optimize, so this is like optimizing 7x versus optimizing 7x plus 23. Okay? If I add a certain constant to my objective function, nothing changes. Any solution that was optimal before remains optimal now, and so on. Okay? So this is a property that's going to be useful in general for network flow problems. We may not exploit it to the extent that it needs to in network simplex, but it happens to be true. Yes. Yes, we are. So we are looking at a pure network flow problem. All the gains are 1. That's an important point. Yes. Okay. So yes.
Where did you get the pi I in the secondary part?
Here?
Yeah.
This is just taking this expression. So remember, for if ij is an arc, okay, then the flow on that arc is going to have a multiple of positive pi I and negative pi j. So here is I, here is j. The flow here is going to have xij times pi I minus pi j. If I have another arc here, k, it's going to have pi I minus pi k times xik, right? Now look at things that enter node I. So this is going to be some L, this is going to be some P, and so on. So this is going to have pi L minus pi I times xli. Pi P minus pi I times xpi. So any arc that goes into node I, that flow value is going to pick up a negative pi I. And any arc that leaves node I, that flow value is going to pick up a positive pi I. So that's why this expression is the same as pi I times the stuff that leaves I minus the stuff that enters I. It's just rewriting an expression in a more convenient way. So, yes, and what's BI? BIs are the external supplies. So what flows out of I minus what flows into I equals the external supply to node I. And of course this could be negative, in which case it's really a demand. The point is that the difference between these two quantities for any flow x is going to be a constant. So it's as though you're taking any flow and adding a certain constant and calling its value in a new problem, this enhanced by a certain constant. So the relative ranking of every solution is going to stay the same. You're just going to measure things differently. Okay. So let's look at the optimality conditions. So suppose you have a flow, and suppose you have a phi, which really is a dual solution. Then you want all of the following to be true for this to be optimal. Okay, so let's see why. So first of all, you want X to be a feasible flow. Okay. Secondly, if Cij pi is positive, then you want Xij to be 0. Why is that? Well, let me put it to you this way. Suppose you have an x and pi satisfying all of these conditions. Then I claim that that x has to be optimal. Let's understand why. So we just saw that optimizing with respect to C and optimizing with respect to C pi are the same thing. Okay? So you can now view your network flow problem as optimizing with respect to this quantity C pi. So the arc flows, the costs are all C pi instead of C. Okay? Suppose you find a flow satisfying all of these. You have a feasible flow. Whenever Cij pi is positive, the flow is 0. And whenever Cij pi is negative, the flow is at its upper bound. Then we claim that this is the best possible. And this should be clear for the following reasons. You want to minimize the overall cost. Okay? Suppose I have a certain Cij pi strictly positive. What is the smallest value that you can set the flow to? Zero, because the lower bounds are all 0. And you tell me that I have to pay you money to send flow, then I send nothing. Okay. So, I mean, if you forget about condition 1 for a moment, this is what you would like to do given a network flow problem, right? Any flow cost that's strictly positive, you would not want to send any flow. And any flow cost that's strictly negative, you would want to send as much as possible because you get paid for sending stuff on that arc. Now, of course, if you only had 2 and 3, you get a certain flow that is optimal, assuming that it's feasible. Why is it optimal? Because this is what you would ideally like. And